Hello and welcome to Advanced Digital System Design playlist. Today we're gonna study about JK Flipflop. What JK Flipflop actually is. The JK Flipflop is basically a gated SR flip-flop with the addition of a clock input circuitry that prevents the illegal or invalid output conditions that occurs when both inputs of S and R are equal to level 1. In the previous video we studied about SR flip-flop, in which case the last condition when S and R were equal to 1, the output showed the not defined condition. Here in JK flip-flop that illegal or invalid output condition is prevented. The JK flip-flop has its name from the inventor Jack Kilby. Here the inputs S and R of the SR flip-flop are replaced by J and K respectively, and the two input NAND gates of the SR flip-flop have been replaced by two 3-input NAND gates with third input of each gate connected to the outputs Q and Q bar. This cross coupling of the SR flip-flop allows the previously invalid condition of S is equal to 1, R is equal to 1 state to be used to produce a toggle action. In JK flip-flop what we have two 3-input NAND gates where the third input of each NAND gate is connected to the output. Like for this NAND gate, the input is connected to Q bar, and for NAND gate 2, the input is connected to the Q. This cross coupling of the SR flip-flop allows the previously invalid condition of S is equal to 1, R is equal to 1 to be used to produce a toggle action. This cross coupling produce a toggle action when S is equal to 1, R is equal to 1. Now for the characteristics table, we write the necessary 8 combinations for JKQN, and we find the QN plus 1, that is the next state. We write the 8 combinations 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. The QN plus 1 is actually the QN plus 1 of the SR flip-flop only. For 0, 0 input we have the QN is equal to QN plus 1, that means the memory state. And for 0, 1 input condition we have a reset state 0, 0, and for 1, 0 input condition we have set state 1, 1, and lastly for when J is equal to K is equal to 1 we have the toggle action here. Unlike in the SR flip-flop, this state was not defined. Here the toggle means Qn is equal to Qn plus 1 bar. Now we can define simplified table from this characteristics table. We write the 4 combinations 0, 0, 0, 1, 1, 0, 1, 1, and for 0, 0 combination we have memory state Qn is equal to Qn plus 1, and for 0, 1 input condition we have the reset stage 0, and for 1, 0 input condition we have set state, and for lastly the 1, 1 input condition we have Qn plus 1 is equal to Qn bar, that is the toggle action. Now in order to determine the characteristics equation, what we do is we usually write the corresponding entries of the Qn plus 1 into the corresponding cells of the K map. In the cell number 1 and 2 we have 0, 1, 0, 1. In cell number 3, 4 we have 0, 0, 0, 0. In cell number 5, 6 we have 1, 1. In cell number 7, 8 we have 1, 0, 1, 0 in 7, 8. After necessary grouping we get the Qn plus 1 characteristic equation, that is equal to K bar Q plus J Q bar. The excitation table of this JK flip-flop can be found by the characteristic table which we have already described. What we do is we write the Qn and Qn plus 1 entries 0, 0, 0, 1, 1, 0, 1, 1, and we see for 0, 0 in characteristics table for Qn is equal to 0 and Qn plus 1 is equal to 0, what we have is we see this 0 0, and we locate another 0 0 which is here 0 0 0 0, and we see the corresponding J and K values. For this 0 0 0 0, and for this 0 0 there is J is 0, K is equal to 1. So J is 0, that is not changing, and K is changing 0, and here it is 1. So we write in the excitation table for J we write 0, and as this is changing we write here don't care. So we write for 0 0 we write 0 don't care. Now similarly for the second entry 0 1, we check the characteristics table 0 1, 0 1 is here, 0 1 is here, and we check the corresponding J and K values. For this J and K values 1 0, and for this is 1 1. So 1 is not changing and this is changing 0 1. So we write 1 don't care in the excitation table. For 0 1 we write 1 don't care. Similarly for 1 0 we write don't care 1. 1 0 is here 1 0, and 1 0 is here. We write here J and K. J is 0, here J is 1, K is 1, K is 1, K is not changing, so this is changing. We write don't care 1 in the excitation table. And for the last entry 1 1, we see 1 1 is here and 1 1 is here. This is J is equal to 0, K is equal to 0. For this K, J is equal to 1, K is equal to 0. So K is not changing and J is changing from 0 to 1. So we write don't care 0 in the excitation table. This completes the excitation table of the JK flip-flop. Now from this excitation table we can determine the corresponding state diagram, which is shown as this corresponding state diagram. We write from the excitation table, that is when the initial state Qn is equal to 0, the next state is 0. For the inputs 0 don't care, we write it as 0 initial state, and the next state is also 0, so there is a self loop. For the inputs 0 don't care for the JK. For the next 0 is the initial value and 1 is the next value. So we draw an arrow from 0 to 1. For the inputs 1 don't care, because here it's 1 don't care for the J and K. Next we have 1 0, 1 initial state, its next state is 0. So we draw an arrow from 1 to 0 pointing towards 0, and for the input value don't care 1 for the JK, because here it's don't care 1. And for the last entry 1 1, we write it as, we draw a self loop at 1 and pointing to 1 only. That means the initial state is 1 and the next state is 1 for the input. Don't care 0 for the JK. Here don't care 0. This completes the state diagram of the JK flip-flop. That's all for this video. I would like to thank you for watching, and please do like and subscribe.
Subscribe now and press the bell icon. Never miss an update.